Hello students, welcome back. In the previous video we talked about matrix multiplication and we were doing this example, I believe. No, this cell here, and we did this example. Other problems are kind of like these. Just first row, first column will give me 1, 1. First row, second column for 2, 2. And third column, if necessary, go. But we don't have any more columns here. Let's go to second row. Second row, first column for 2, 1. And the second row, second column for 2, 2. And so on. That's how you do matrix multiplication. Now here's a special case. What if we have a column vector? This appears a lot actually. So we have m by n times n by p ends up m by p matrix. But p is 1 here, then consequently we are going to get p is 1 there. So we always end up with a column vector. So n-dimensional column vector n by p will become m-dimensional column vector m by p, depending upon what you multiply. Here's an example. This matrix is, let's see, what by what matrix is it? How many rows? Stop this recording and then answer. 4 by 3 matrix. And this one is 3 by 1 matrix. And then this number here, which I just highlighted in red, and that number there are the same. So we have 4 by 1 matrix, and in the end, yes, we have 4 by 1 matrix. And how do you do the computation? First row, first column. Here we go. Dot product computation. And then second row, first column. And then this dot product computation. Third row, first column, we have third, and so on. We have 4 rows here, so we'll have to repeat it 4 times. And please note this, by multiplying this matrix, m by n matrix, this n-dimensional column vector went to m-dimensional column vector, so you can regard matrix multiplication kind of like this. M by n matrix, and let me expand the font here so that you can see subscripts a little bit better. Basically, this is acting like a map. Like this. N-dimensional column vector is being sent to m-dimensional column vector. That's what this matrix multiplication is doing. So you can consider matrix multiplication as a map. It's a linear map, and we can consider, oh, never mind, I'm getting a bit too deep in there. And the reason I just mentioned it is because that aspect will show up in lesson 15, and a lot of students may just skip the latter part. That's why I mentioned it. I wanted to tell it to everybody. Okay, here's final example here, and that's a non-example as a matter of fact, undefined. Let's see, we have 3 numbers here in this row. Here I have 3 numbers. Up to here well defined. First times first, second times second, third times third, and we can add them up. But what about this fourth third? That one doesn't have any pair, so this multiplication fails. You see, this n and that n have to be the same, otherwise matrix multiplication is undefined. Okay, so much for matrix multiplication. And we did some demonstration as well. Now, identity matrix. This matrix is called identity matrix because it works as the multiplicative identity of matrix multiplication. Here's an example. This is I, the identity matrix. You see, we have ones in principal diagonal, the others are 0. Times a certain matrix is self. And please check the computation here. So this matrix works exactly like multiplying by 1. Now, does it work for left-hand side? How about the right-hand side? Well, it works well, yes, but a little bit of a wrinkle here. So multiplying by an identity matrix to the right, also I get the same matrix back, but it's not this identity matrix, a little bit different identity matrix because we need different size. We have 2 columns here, so we need only 2 rows, so this has to be 2 by 2. Previously, we had 3 rows, so we need 3 columns here, so that we have 3 by 3. If you have square matrix, if you begin with a square matrix, then you don't have to worry about this at all. I times A is A times I is A, and they commute. But for general rectangular matrix m by n, that's a bit different story. By the way, this is the component expression of identity matrix, and typically we use delta ij, named after German mathematician Kronecker. We call it Kronecker delta. And whenever you see delta ij, consider it as identity matrix. So the principal diagonal is all 1, everything else is 0. So I and j are the same, then 1, otherwise all 0. That kind of thing is called Kronecker delta, and it is associated to identity matrix. Okay, now we got the third algebraic operation done. So what about the algebraic rules associated to matrix multiplication? Here we go. They all make sense except one. Associativity, okay, that makes sense. Multiplicative identity, A times I is itself, I times A is itself, yes. Distributivity, all right. And I don't know whether this can be called associativity or commutativity or what. Actually, it means the scalar multiplication A can be multiplied anywhere, before or after, or up to B, up to C, or if A can be factored further, partly to B, partly to C. You can do all kind of things to scalar, because that's scalar. But as for matrix multiplication, here's a big wrinkle here. The commutativity fails. A times B and B times A are not always equal. And that's important. Because some of those techniques that we'll have to apply here in differential equations require this commutativity, and consequently you'll have to do those for rather special matrices only. Well, here are some counterexamples here, but that's not really important. I mean, this is not linear algebra class, so we're not going to go into proof or disprove that kind of things. Just remember the commutativity fails. And multiplicative inverses do not always exist, so there are some matrices that cannot be divided, basically. And zero divisor property, that's another interesting property. A times B is equal to 0, then either A is 0 or B is 0. That works for real number arithmetic and also for complex number arithmetic, but for matrices, no, it doesn't work. So be careful about those, especially the first one, commutativity. As for transpose, yeah, and you have to switch the order of multiplication. It's simple, but I don't know whether we are going to be using commutativity, whether we are going to be using transpose at all in this course. So let's just move on to the next topic, inverse matrices. What do you mean by inverse matrix? Basically, it's division. Let A and A inverse, not A to the negative first power, we call A and the other matrix B square matrices of same sizes, and A times that matrix equal to I. Also, that matrix times A is also I. If that kind of matrix exists, we'll say that matrix is the inverse matrix of A, and we'll denote it as this negative first power like this. If such matrix exists, then A is said to be invertible. Not all matrices are invertible. We saw some examples. I think it's what's already there. Yeah, this matrix in particular does not have any inverse, even though it's not a zero matrix. And of course, there are many more, infinitely many examples there. Okay, non-invertible matrices. Oh, okay, examples already there. Inverse rules. Just like transpose, AB inverse is same as B inverse times A inverse, but I don't know whether this is going to be really important for our course. In linear algebra, it's important. Double inverse is itself, that's easy, and if you divide twice, then, reciprocal twice, then you get the original. Similar matrices, no. Here's an important formula that everybody should remember for this course. Inverse matrix formula for 2-dimension. For 3D or higher, the formulas are too complicated, it's difficult to follow, but for 2-dimension, everybody should remember it. How does it work? Invertible if and only if AD minus BC is non-zero. If that's zero, then this is invalid because something will have to go to the denominator here. And this quantity, by the way, is called the determinant. And the determinant for a 2x2 matrix is AD minus BC. And the inverse formula goes like this: 1 over AD minus BC, and then switch the principal diagonal, and then put negatives to the others. If you want to prove, actually the proof is really easy. Just apply the matrix multiplication and you're done. First row, first column, then you get AD minus BC. First row, second column, you get DB minus BD, and that's 0. And first row, second row times first column, minus C plus AC, that's 0. And finally, second row times second column, again we have AD minus BC. So dividing by AD minus BC, we get identity matrix. The proof is actually just brute force computation, and there may be some students who are relatively new to matrix multiplication. That's why I slowed down and did all those. I think for majority of the students, they either took linear algebra already, or they must remember matrices from pre-calculus courses. Here's an example. Find the inverse of this matrix. Just put it into this formula, AD minus BC, multiply, crisscross, -3 minus 12. Okay, it goes like this. Crisscross, AD minus BC. We get -3 minus 12, so -1/5. 1/15th, excuse me. That's the scalar multiplication part. And as for the matrix part, switch the principal diagonal and then put negatives to the others. And that's what we have here. You can simplify it a little bit further by removing the negatives because there are too many negatives are flying around, but that's not really necessary. You could have stopped here if you wanted. That's how you find matrix. That's how you find inverse matrix. Okay, how about the next example? Find the inverse of this, and it'll turn out this is not invertible. And you can clearly see that because if you put it into this inverse formula, you get 1 over 0. The determinant, AD minus BC, is 0, so everything falls. This quantity, AD minus BC, is called a determinant for 2 by 2 matrix. So 1 over determinant times switch the principal diagonal, and the others are minuses. So remember this inverse matrix formula. Okay, that's about it for our first section, and we're going to discuss section 2 in a separate video.